Hello everyone and welcome to chapter 6. Today we are going to dive into a really important topic in physics, energy, and how it applies to systems, including something you have all seen before, oscillations. Now before we jump right into energy, let's start with the idea of work. Have you ever said, wow, that was a lot of work? After moving a furniture, carrying groceries, or even pushing your car when it won't start. So in physics, we define work in a very specific way, and it's not always the same as our everyday meaning. So here's a question for you to think about. If you hold a heavy box completely still, are you doing work on it in the physics sense? You might feel tired, but is there actual work being done? Hold on to that thought. We will clear it up very soon. So once we understand work, we will see how it connects to energy, which is one of the most powerful and unifying concepts in all of physics. And then we will take it one step further and explore how energy shows up in oscillations, like swinging pendulum and a bouncing spring. So now let's take a look at the learning objectives for this chapter. Alright, let's map out what we are going to cover in this chapter. First, we will start with the idea of work, what it really means in physics and how we define it. Next, we will see how this concept of work connects to changes in a system's kinetic energy and potential energy. And from there, we will bring these pieces together to introduce one of the most powerful tools in physics, the principles of energy conservation. And finally, we will apply all of this to real-life situations, like the motion of a simple pendulum, to see how energy ideas make analyzing motion much easier. So by the end of this chapter, you should not only understand these concepts, but also be able to use them in problem solving. Here's a quick overview of what we will cover in chapter 6. We will begin with simple machines, work and power. Then move into kinetic energy and potential energy. And after that, we will bring those ideas together with the conservation of energy principle. And finally, we will finish the chapter with springs and simple harmonic motion. So this outline gives you the big picture of where we are headed. So before we dive into this section, let's try a simple thought experiment. Imagine you make a pendulum, just a ball tied to the end of a string, like you see in this figure. Now let me ask you, how do you get it to start swinging? In other words, how do you get energy into the system? So you need to pull the ball away from the center and then let it go, just like pushing a swing chair at the park. So from a physics perspective, what you have really done is apply the force on the ball and move it through some distance with your hand. And that's what we call work in physics. Now notice what happened. By doing work, you have given energy to the system. And now the pendulum has the energy it needs to swing back and forth. So this is the basic idea. Doing work is a way of transferring energy into a system. So now that we see how this works with the pendulum, let's move on and see how simple machines use the same idea of work. Alright, now let's talk about simple machines. A simple machine is any mechanical device that multiplies the effect of a force. Examples includes levers, pulley systems and inclined planes. Now take this lever as an example. If you apply a small force at one end, this end, a larger force can act on a heavy object like a rock at the end. So that's what we mean by multiplying the force. It makes the work easier for us. But how does this really work? Well, to get a larger force, we need to apply a smaller force over a larger distance, smaller force over a longer distance. And that force then moves the heavy object a smaller distance but more effect. So the key idea with simple machines is smaller force over a larger distance gives a larger force over a smaller distance. So that's how we make hard tasks easier using mechanical advantage. Now let's look at another example of simple machines, the pulley system. So how does this work? Imagine a rope running through a pulley and you pull on one end. So by doing this, you are applying tension to the rope. So in pulley setups, this tension can multiply, making it easier to lift a heavy object at the other end. For example, in this system, you can lift a box a certain height by applying a force equal to only half of the weight of the box. But there's a trade-off. You have to pull the rope twice the distance that the box moves. So if the box moves a distance of x, then you have to pull the rope a distance of 2x. So just like with the lever, the idea is a smaller force applied over a larger distance gives a larger force over a smaller distance. And notice something important here. If you multiply the force by distance, it's the same on both sides. This is the concept of work. Work input is equal to work output. There's also a term for the ratio of the output force to the input force. And this is called the mechanical advantage of a simple machine. So for this pulley system, can you guess the mechanical advantage? It's 2. So this shows us clearly how simple machines make work easier without violating the physics principle of energy conservation. Alright, now let's review what we meant by work in physics. Alright, now let's review what we mean by work in physics. Work is basically the product of the applied force and the distance over which the force acts. So in symbolic form, we write it as W equals to Fd. W means work, F means force, D means the distance. And the unit of work is Newton meter. So force is in Newton and distance is in meters. So the unit of work is Newton meter. And in the metric system, we call Newton meter as joules. So 1 Newton meter is equal to 1 joules. So for example, imagine you push a heavy crate across a concrete floor with a constant horizontal force like in this figure. The work you do is simply the force times the distance you move the crate. And notice, the farther you move it, the more work you do. Now here's a question for you to think about. What if the force is not exactly in the direction the crate moves? So if the force is applied at an angle, then only the component of the force parallel to the motion contributes to the work. Only the force parallel to the direction of motion contributes to the work. So why? Because the perpendicular component, like the normal force of gravity, doesn't actually help move the crate along the floor. It has no effect in producing motion in that direction. So the key idea is only the part of the force that acts along the direction of motion does work. Alright, let's try a simple exercise to see this in action. So we have a crate being pulled 4 meters across the floor by a rope. The force applied by the rope is 50 Newton. Now what is the work done on the crate by this 50 Newton force if the rope is horizontal? So that means it is parallel to the floor. That's part A. And in part B, if the rope pulls at an angle to the floor. So give a try to solve this. So these are the given parameters in the question. The applied force, which is 50 Newton, and the distance, which is 4 meters. Now remember the formula for work? W equals to F D, force times distance, right? Now here the full force acts in the direction of motion. Therefore W equals to, force is 50 Newton and the distance is 4 meter, which gives you 200 Newton meter or 200 joules, right? So in part A, force is applied in the direction of motion, right? So you have done 200 joules of work. Now in part B, the rope is at an angle and the horizontal component of the 50 Newton force is only 30 Newton. So you have a 50 Newton force and the horizontal component of this 50 Newton force is 30 Newton, and you move this crate a distance of 4 meter. So in this case only the force parallel to the motion does work. So we use the horizontal component. Therefore work done is the horizontal component of force times the distance. So here horizontal component is 30 Newton and the distance is 4 meter. Therefore work is 120 Newton meter, or it is 120 joules. So when the rope is angled, the work done is less, 120 joules in this case. So what we see from this example is that by doing this work, we have transferred 200 joules of energy from the person applying the force to the crate and its surroundings. So the person loses energy and the crate and everything it interacts gains energy. And remember, whenever we calculate work, we always use the component of the force in the direction of motion. So in this case, that's the horizontal component of the applied force. So the key takeaway here is that the direction of the force matters. Only the component along the displacement contributes to work. Now that we have talked about work, let's introduce power. Power is basically the rate at which work is done. In other words, it tells us how fast you are transferring energy. Mathematically, we write it as P equals W over T. P means power, W means work, T is time. And the units of power is joules per second. We call it watt. Work is in joules, time is in seconds. Therefore, the unit is joules per second, or we call it watt. So that's the metric unit or the standard unit of power. And there's also another unit you might be familiar with, especially when talking about car engines, the horsepower. So 1 horsepower is equal to 746 watts or 0.746 kilowatts. Now notice from this equation, if you do the same amount of work faster, the power increases. So lifting a box slowly requires the same work as lifting it quickly. But the faster lift requires more power. Alright, now let's go through a few examples to see how all these ideas, work, energy and power, play out in real situations. Here's a quick conceptual question to test your understanding of work. A string is used to pull a wooden block across the floor without accelerating it. The string makes an angle with the horizontal. The question is, does the force applied via the string to work on the block? Now pause the video for a moment and think about your answer before moving on. So the correct answer is C. Only part of the force does work. Why? Because in physics, only the part of the force that acts along the direction of motion contributes to the work. Only the part of the force that acts along the direction of motion. So in this case, that's the horizontal component of the force. So the vertical component doesn't move the block along the floor. It doesn't do work. So remember, whenever a force is applied at an angle, only the component parallel to the displacement counts towards work. Now let's look at the same diagram again. But now, imagine there's a frictional force opposing the motion of the block, a frictional force. So the question is, does this frictional force do work on the block? So again, pause the video for a moment and think about your answer. So the correct answer is yes, the frictional force does work. Why? Because the frictional force is opposite to the direction of motion. So when a force acts opposite to the displacement, it does a negative work. It takes energy away from the moving block. So remember, forces that oppose the motion always do negative work, reducing the energy of the object they act on. Therefore, the answer is A. The frictional force does work, but it's a negative work. Now let's think about the normal force, the flow pushing upward on the block. Normal force. So does this force do any work on the block as it moves horizontally? Remember, the box is moving in the horizontal direction. Okay? And the normal force is in the upward direction, which is in the vertical direction. So does it do work? So the answer is B. The normal force does no work. Why? Because work depends on the part of the force that acts along the direction of motion. Here the normal force points up, but the block moves sideways. So the force is perpendicular to the motion. So no work is done, right? Now let's try a real calculation. A 50 Newton force is used to drag a crate 4 meters across a floor. The force is applied at an angle upward from the horizontal, like in this diagram. So our question is, what is the work done by this horizontal component of the force? So the horizontal component of the force here is 40 Newton. That's the horizontal component of the 50 Newton force. So before we calculate, what do you remember about work? What's the formula for work when the force is at an angle? Again, pause the video for a moment and think about your answer before moving on. The answer should be B, 160 joules. Why? Because here we are considering only the horizontal component of work, which is 40 Newton, which is along the direction of motion, right? Therefore, work is force times horizontal component of force times distance. And here, horizontal component of 50 Newton force is 40 Newton and the distance is 4 meter. This is the distance. Therefore, the answer is 160 Newton meter, and we know that Newton meter is joules. So the answer is B. Now we just calculate the work done by the horizontal component of the force. But what about the vertical component? What is the work done by the vertical component of the force? What do you think? The correct answer is E, 0 joules. Why? So even though the vertical component is 30 Newton, it has a certain value, it is 30 Newton. But the displacement of the crate is completely horizontal, right? It doesn't move in the vertical direction. So the displacement is completely horizontal. So work depends on the part of the force in the same direction as the motion. And since the vertical component is perpendicular, it does no work. The distance is 0 meter. Therefore, work is 0, right? Okay, we have talked about the horizontal and vertical components separately. Now let's put it together. What is the total work done by this 50 Newton force? What do you think the answer is? The total work done by the 50 Newton force. The correct answer is B, 160 joule. Remember, only the component of the force in the direction of motion contributes to the work. And that's the horizontal component, 40 Newton joules. Right? So it is 40 newtons times 4, which is 160 joules. So what's the big idea here? Even though the total applied force is 50 Newton, the vertical part doesn't count in this situation because it doesn't move the crate. Only the component along the motion matters for work. Okay, great job everyone. With this great example, we conclude the first section of the chapter 6. So key takeaways are work is force times displacement and power is the rate of doing work. And always consider the parallel component of the force in the direction of motion when calculating work. Now let's move on to the next section, kinetic energy. So if work is done on an object, where does that energy go? For example, if I push a crate and it speeds up, what kind of energy is increasing? So we will explore it in the next section.